The third of four transformations that we're going to take a look at is stretching and compressing, literally taking a function and stretching it up or squishing it in. So a stretch and a compression do exactly what they say. They stretch or compress an equation. Formally, a stretch or compression is defined as follows. Again, we're using this value of c, and we're saying that it is the factor by which we are stretching. Notice what we do with that value of c. Our function here says y is equal to c times f of x. What that's communicating is this. In order to stretch or compress a function, all you do is take the entire function and multiply it by a value that we're calling the factor of stretch or compression. Now, intuitively, hopefully this makes sense. If the value of c is greater than 1, it's going to stretch the function out. If the value of c is between 0 and 1, it's going to compress it. Now keep in mind that this stretching and compressing is done in the y direction, not the x. So it's going to take it and either squish it from the top and bottom, that's a compression, or pull it out from the top and bottom, that's the stretch. So let's look at our first example here of a stretch. We've got the original function y equals 2/3 x minus 4. So I'm going to plot that, y-intercept of -4, and then we've got our slope of 2/3. Got my points right here, I can connect these, and here's my line. Okay. Now the question is, how do I take this and stretch it by a factor of 2? Well, that formula said all I do is take my function, f of x, equals 2/3 x minus 4, and I take my entire function and I multiply it by 2. So what does that turn into? F of x equals, this 2 gets distributed into both pieces, so that becomes 4/3 x and then a minus 8. So here's my new equation that has been stretched by a factor of 2. Let's see what happens and see what this ends up looking like. My new y-intercept is at -8, and my new slope is at 4/3. So up 4 over 3, up 4 over 3, up 4 over 3. So the question is, that graph looks like it's just been rotated. Why is it a stretch? Okay, and here's how we need to view it as a stretch. Every single value I look at, let's look at this value right here. I'm down at -2, but my new equation is down at -4. Here I'm at -4, but my new equation is down at -8. Here I'm at 2, but my new equation is up at 4. Can you see how every single y value, remember the stretching or compression happens in the y direction, every single y value is now twice as big as it used to be. Notice that the x-intercept didn't have anything change about it. That is because the x-axis is what everything is stretching up or down and away from. The x-intercepts never change with a stretch or compression. So let's look at stretch and compression in the context of an exponential. Here I've got 3 times 1.34 to the power of x minus 4. So my horizontal asymptote is down here at -4. And let's see, if I work it out, again, I'm not going to spend a lot of time in these videos working things out for the graphing. Working it out already, I found out that my y-intercept is -1. So that's at 0, -1. And my x-intercept is at 0.98. So that's 0.98, 0. And because this is greater than 1, the 1.34, I know it's growth. So it's leveled off on the left. It climbs up and grows through my x and y intercepts. So what does it look like to stretch this by a factor of 1/2? Well, we take the equation and we multiply the entire equation by 1/2. So that's 1/2 times 3 to the 1.34 to the x minus 4. So what I'm going to do is I'm going to take this and multiply this 1/2 into both terms. That produces g of x is equal to, let's see, 1/2 times 3, that would be 3/2, times 1.34 to the power of x, and then 1/2 times -4 is -2. So here is my new equation stretched by a factor of 1/2. Now, if I'm stretching by a factor of 1/2, is it really a stretch? Well, the answer is no, it's actually a compression. So what has happened? Interestingly enough, take a look at this. Where is my new horizontal asymptote? It's at -2. So it looks like the distance that my horizontal asymptote is away from the x-axis has been cut in half. It was at -4, now it's only at -2. Furthermore, if I work it out, I'll find that my new y-intercept, instead of being down at -1, is at -1/2. So 0, -1/2. Again, it is half the distance from the x-axis now. I was at -1, now I'm at -1/2. My x value does not change at all. So the new equation, or the new graph, ends up looking like this. Everything has been squished towards the x-axis. It's been made flatter with the x-axis. So there's a compression by a factor of 1/2 on an exponential equation. Next, we want to look at it in the context of a quadratic equation. It's quadratic because I have an x squared term. So, looking at this quadratic, I know that my vertex is at the point 3,5. So I'm going to draw that right there. I know that it also opens downwards because of the negative in the front. And then I've already worked it out. I found that my x-intercepts were at 5.24 and 0.76. So this is 5.24, 0, and this is 0.76, 0. And up here, this point is the point 3,5. I also figured out that my y-intercept was at -4. So 0, -4. And I open down like that. So there's my original graph. But what is it asking me to do? It's asking me to stretch by a factor of 1.5. So I have to take my function here, and I need to multiply the entire function by 1.5. So that's 1.5 times negative x minus 3 squared plus 5. Taking this 1.5 and distributing it in produces f of x is equal to negative 1.5 times x minus 3 squared. That's into this first term. And then into the second term, 1.5 times 5 is 7.5. 7.5. Okay, so now let's take a look at this. Here is my new equation of my that has been stretched by a factor of 1.5. What does the new graph look like? So what we find when we look at this is our new vertical asymptote is at 3, 7.5. So 3, 7.5. Taking a look at that, what happened? If I look at my y value of 5 right here, what is 5 times 1.5? It's 7.5. So it's stretched it up by a factor of 1.5. Now, what's nice is, what we've already seen, x-intercepts stay exactly where they're at. But now, where is my -4 at? Well, my -4, interestingly enough, moves down to a -6. Why? Because what is -4 times the 1.5? Stretching it away from the x-axis by a factor of 1.5. Well, -4 times 1.5 is -6. So this point has moved down to 0, -6. and my vertex has moved up to 3, 7.5. So it's taken and it's stretched this out vertically. Everything stays the same on the x-axis, but everything else has been stretched away from the x-axis, either up or down. Our last example is a radical equation, and we're stretching this by a factor of 1/4, which again, because it's less than 1, it's a compression. So let's graph this original equation. Looks like my starting point is at -2, 4. So -2, 4 is right here. I've already worked it out, and I found that my y-intercept was at 2.59, and my x-intercept was way out here at a 14. So I'll just put a point way out there towards the edge. So starting point, this comes down, and then through that x-intercept. Let me label some stuff here. That's -2, 4. This point right here is 0, 2.59. Good. Now we want to stretch by a factor of 1/4. So to find the new equation, I simply take the original one and factor it, or rather not factor it, but multiply it by that factor of 1/4. So 1/4 times that entire equation produces my new stretched, or rather compressed function as -1/4 times the square root of x plus 2, and then plus, that was this distributed into that first piece, distributed into here, 1/4 times 4 is 1. So here is my new equation compressed by a factor of 1/4. Where is my new starting point? My new starting point is at -2, 1. So -2, 1 is right here. Okay. Notice that my original starting point was up here at a 4, but my new starting point is at a 1. It has been cut, or it's been multiplied by a factor of 1/4. It is 4 times closer to the x-axis than it originally was. We know that our x-intercepts don't change, but what about my y-intercept? I'm going to simply take my 2.59 and multiply it by a 4th, because my new y-intercept should be 4 times closer, and I end up getting a 0.65, and this point out here was -2, 1. So what it's done is it's just squished it closer to the x-axis by a factor of 1/4. Every point is 4 times closer to the x-axis because we multiplied it by a factor of 1/4.